As Paul mentioned, this is my part of I guess, an ongoing series of lightning talks where folk from Alembic choose a problem from the Exercism website and then complete it and then do a little write-up. So mine's about complex numbers. So first off, we probably need an introduction to complex numbers because it's possible that you all know them, but it's also possible that maybe there's somebody out there that's not familiar with them. I don't know how ubiquitous they are, I guess, amongst the general population. I imagine amongst coders, maybe a little bit more frequently known, but we'll go over them. So we'll first discuss, I guess, the essential part of complex numbers, which is the imaginary unit I. We're all familiar with ordinary, what we'll from here on out call real numbers, where if you square a real number, you always get a positive real number back. And that just seems like a truism, like it seems like that really should be inevitable. But mathematicians, being like they are, that didn't stop them. And so they discovered or came up with, depending on what your particular philosophy is, came up or discovered a number which they call I, which is called the imaginary unit, and has the unusual property that if you square it, you get a negative number. In particular, I times I equals -1. And you can combine this imaginary unit with the real numbers to get a larger set of numbers. So the way you do that is basically using the normal rules of multiplication and addition that you'd have for real numbers. You combine it and you perform all the same rules, such as just the distribution, commutation. I should have written these down. So distribution is where if I have two numbers A plus B, then I times that section by R, and that is RA plus RB. And then commutation is something like AB equals BA. So you swap them around, they commute. And then association is like A times, and then in brackets BC is the same as in brackets AB times C. I don't know if that made sense for my verbal description. So again, I guess the idea is all these operations like multiplication and addition are always binary. You're always taking two inputs. So association is just saying you can change the order in which if you have three numbers that you're multiplying, say A, B, C, you can either multiply AB first and then C, or you can do BC and then A. And so with that, combined with the fact that I squared equals -1, you can create these complex numbers. So I've shown how here I've got two complex numbers. The way they're often written is as a real number A, for example, plus a real number B times the imaginary unit. A equals 0, in which case you just have an imaginary number like BI. So 3 times I would be an imaginary number, but it's still a complex number because in that scenario, A equals 0. Similarly, the real numbers are just a subset of the complex numbers in which B is set to 0. So in this case, I've got A plus BI times C plus DI. So there's two different complex numbers. And when you follow those laws that I mentioned before, like the distributive laws and commutative laws and associative laws, you get this expression. And the important takeaway here is even after multiplying these two complex numbers, you get a number which is still in the same form as before. So you've got a real number here, which is AC minus BD, and then you got another real number, BC plus AD times I. So the takeaway here is you can define a complex number as a tuple pair, in which the two elements in the tuple are floats. Okay. So this is kind of like the first, and I guess non-elixir, in some sense, non-elixir way of getting the real and imaginary part. So because it's a tuple, we want if we go back here, we want the first, and then for the imaginary one, we want the second. And so that's what I've done here. I've done LM A, and then a position 0, and then for imaginary at position 1. However, of course, Elixir has pattern matching, so you can rewrite that. In that case, you just pass in the tuple, and then you just like do that. It's very easy. That'll be a common theme, I guess. So I could have rewritten it each time, but it doesn't seem necessary. The general gist is I'm going to do pattern matching where I can. Okie doke. So multiplication following, what have I done here? Oh yeah, so here I've following that formula that I showed you before on the previous slide for multiplying two complex numbers out. I've inserted those, except I'm calling the functions I've defined before for real and imaginary. However, again, I can just use pattern matching, and I don't need to do that. I can just literally call the values straight off. So in the lower line is just the AC minus BD for the real part, and AD plus CB for the imaginary part, and I return it in a tuple. Addition and subtraction is pretty easy, even easier than multiplication. Again, pattern matching, except this time we're adding in the first elements and then putting it in the first part of the tuple, and then likewise for the second for the imaginary part. For subtraction, very much the same, except of course now we're minusing the second. So it's A minus C and then B minus D. Conjugate might sound a bit scary, but it's not that scary. Basically, like I said, any complex number can be expressed as A plus IB, where A and B are real numbers. So conjugation is literally just flipping the sign of the B, basically. So A plus IB will go to A minus IB. Oh yeah, and that's my code again, just pattern matching. This part's getting maybe a little bit hairier for those who aren't familiar with maths. So another aspect of complex numbers is any complex number can be represented in this form, where R is a real number and T is a real number, but what's different here is it's R times E, and E is a mathematical constant. I can't remember the exact value of it. It's like 2.7 something, blah, blah, blah. So E is like one of those super important mathematical constants like pi. It's probably up there with pi, if not as important as pi. But basically, it's E to the power of I, which is the imaginary unit, times a real number. So got two real numbers again, which is unsurprising. So before we had our complex numbers parameterized by two real numbers. Again, we've got it parameterized by two real numbers, but in a different form. And the connection between these two forms is here with Euler's formula. So for example, if I forget about the R in front of it and just concentrate on the T, the E to the power of IT is this expression, cos T plus I times sine T. And again, if we look at this, we can see it's back in the old original form where our A is equal to L cos T, and then our B is equal to sine T. So what am I saying? So basically, so the next problem in the exercise was to do exponentiation, in particular, that natural constant E to the power of some arbitrary complex number. So for some arbitrary complex number Z, E to the Z, that's the same as E to the A plus IB for some values A and B. And then you can kind of, due to the rules of exponentiation, you can kind of refactor that to be E to the A times E to the IB. And then using Euler's identity that we just saw, we have E to the A times cos B plus I sine B. And so with that, what I do there is I multiply, because it's just multiplication. I use the previously defined multiplication that we did a while back. And I pass in two complex numbers in the form of two tuples. One is a real number, which is to say it's just an entry with the first, so it's just a tuple with the first entry field and then a 0 in the second entry to denote the fact that it's just the real number. There's no imaginary component. And the second number is this second part here, the cos b plus I sine b, which is we've just got a cos imaginary part and then the maths and then the sine imaginary part. Originally, not up to the part where I thought it was. Okay. So, okay, yeah. So to do division, it's a little bit trickier, I guess. I guess this is a bit full on, but I'll try and go through it. Let me just move this. So, okay. So one way of doing it, and this isn't actually the way I actually ended up doing it, but I thought I'd go through it anyway, because it's in some sense the most obvious way. So first of all, you would define an absolute value function that takes a complex number and returns R. So here I've got the complex number. Like I said, it's a complex number is always parameterized by these two real numbers. One, in this case, so I'm using the other version, which uses the exponentiation. So I've got R here, and then I've got the e to the it. So I want it to get that R. And the way to do that would be, as in the most direct way from this direction would be to use, basically you'd need to use a square root function. You take the a and the b values and you do a squared plus b squared, and then you have to take the square root. I didn't end up doing that though, because I couldn't figure out how to get square root going for a while, because I forgot I'd been doing TypeScript for a while and couldn't work out why it wasn't working until finally I figured it out. I was trying to do TypeScript in Elixir, but by the time I figured that out, I'd moved on to another method. But I'll just quickly go through how you might do it in this way. So having computed R for each of the values, A and B, I should probably say it's a bit confusing here. In this case, I'm not using A and B to denote the different parts of a single complex number like A plus IB. I'm actually referring them to two distinct complex numbers. I probably should have changed that to something less confusing like X and Y, but just for this context, know what's going on there. So get the two values, absolute values, which I've got a subscript for RA and RB, and then define the whole complex number by that absolute value for both instances. And then you will have two complex numbers of the form that you can see here. So with that in mind, if you follow this maths here, it's pretty scrunched up. I'll quickly try and go through it. A divided by B, I've rewritten that, except now I've written that form. So I've got R subscript A times e to the power of I t subscript A, and then likewise, except for B, except it's divided. So it's just mimicking the same pattern there, A divided by B. Then the second expression, I've just factored out the RA divided by RB times e to the power of I, and then it's e to the power of I ta divided by tb, which is the same as e to the I ta minus tb. That's just the rules of exponentiation. And then finally, using that rule again, Euler's rule, RA divided by RB times cos Ta minus TB plus I sine Ta TB. And then with that, we can see that we'd get a tuple in that following form, just corresponding to the complex number. So that's one way of doing it, but there's another way without having to do that, and you don't have to use trigonometry, just good old algebra. So, okay, in this case, I've gone back to using A and B as the actual kind of parameters for the complex number rather than being individual complex numbers themselves. So in this instance, A and B are actually real numbers. Likewise with E and F and C and D. Now, consider what division actually means. It means we've got that complex number there divided by that complex number there, giving us that complex number there, which means we can rearrange it. And when we do, we get the following expression. So in other words, the real number e is equal to a times c plus bd divided by c squared plus d squared, and likewise f is equal to, you can see on the right hand side where I is bc minus ad, all divided by c squared plus d squared. And so again, using pattern matching, I've just returning that value for division. In that case, how will we do absolute value? So absolute value and the relation between absolute value and division is in some sense reversed in the instance in the scenario I first showed. In the first scenario, we first would have defined absolute value and then use that to define division. But in this case, I've used division and now I'm going to define absolute value from that. So how do we do that? Again, hopefully this is all like getting very repetitive, but that way it'll sink in. For some complex number z, this time I was smart and I used a different letter rather than a and b to make it less confusing. Z, so ez equals, again, the same expression for r and t, both being real numbers. Now, if we happen to have what e, just e to the power of it was, we could do the following. We could take that z, which is r to the eit, divided by e to the it, and then just using some, hopefully it might look maybe a little messy and scary, but it's actually quite basic. We factor out the r and then times it by e to the it divided by e to the it, which is of course 1. So that just ends up equaling r. And then, so with that in mind, okay, consider again what r to the eit equals. It is again using that Euler's formula. Technically, it's not exactly Euler's formula, but it's related. So we're going to have r cos t plus I r sine t, and then we can use that fact to get a divided by b. So a divided by b ends up equaling sine t divided by cos t, which is the same as tan t, which stands to reason that t equals arctan, which is like the inverse of tan, arctan tan t, or in other words, arctan a divided by b. And that's what I've ended up doing here. So first of all, in this function here, I compute the angle. So I get the imaginary part of a. And I just realized I could have done pattern matching here rather than calling a function, but I guess I forgot to change that one. But here, so I've got imaginary part a and a real a, and I've divided them, and then I'm calling this a tan, which is the inverse of the tan, and that gives me the angle. After that, I use that technique I just mentioned, where I used, again, previously divided function for division, where I pass in a and then divided by the cos of that angle we just found and the sine of that angle we just found in tuple form. So in other words, that's our complex number. And then finally, I pass that to an absolute value, and that will give you the absolute value r of the complex number. And I think that might be it. Yep, that's the extent of my talk.
Cool, thanks, Nick. Looks like you went through a few iterations with regards to the mathematical formulas before you got, for certain ones, before you got something that you were happy with. How many times did you have to do that with the code? How many iterations of code, like to solve, say, one of these particular functions, did you end up doing before you were happy with your solution?
Getting to pass was, I guess I figured out what I wanted to do before I coded it. So getting to pass was pretty straightforward. I guess the iterations mainly came from like refactoring it. So I used pattern matching, I guess. So as you can see in this last one, I forgot to change it there. I could have used pattern matching here, but I missed that one. I guess the biggest challenge was when it came to trying to do the code was trying to work out why my square root function kept breaking the the compiling. And so I moved on to that second version, and then I finally clicked why it wasn't working. It's because I was doing TypeScript. That was probably the biggest obstacle in the whole process.
Cool. Was there anything Elixir-wise that you kind of like learned as a result of doing this particular exercise that that you didn't know about before, or that you kind of thought, oh, that's pretty cool?
I'd say all the things Elixir related I kind of was familiar with is like I really like pattern matching. I've come to really kind of appreciate that. I guess there's one thing I haven't, I don't think I put it there. So with absolute value, I actually defined an instance where the real is 0. So you know how in Elixir you have like one definition for a function, and then you kind of go down the list as you kind of exclude, like as in it goes from less specific cases, I guess. So the first instance for absolute would have included an instance. In that case, I did use pattern matching because I had to use pattern matching. I used an instance. It was for the instance where the imaginary part, sorry, the real part was 0, because if I try to do it in this definition, that will obviously break it because I'd have a division by 0, which you can't do. But I'd say there was nothing necessarily too unfamiliar when it came to Elixir. I guess I could have picked a more Elixir heavy problem. I guess I kind of picked this one just because I got a bit of a maths background, so I kind of was attracted to this one. But it was still very fun kind of using Elixir to solve this problem.
Sure, cool. Did you end up submitting your solution up to the Exercism site and have a look at the community solutions there?
I had a quick glance at the community solutions. I just was curious to see which approach they used when it came to division, and I saw a mixture. I saw one that used the one I use, and then I saw one that used the square root as well, I think.
Cool. Has anyone got any questions for Nick?
I spotted something. I was like, hey, you don't need to use that kernel in front of the absolute function. And then I looked at the definition of your function and realized, yes, you do.
Yeah.
Did it take you a while to figure that one out?
I think that was okay. I guess I knew I was
redefining the kernel function.
Yeah, or
I'd never run into that situation personally.
Yeah, look, I guess it looks a bit odd, but that was their the name that they were calling it. So
yeah.
Are there any other like clever encodings of a complex number other than a tuple? Like, can you pack it into like a binary or something?
How would you do that? I'm not quite sure I know how you might do that.
Well, I'm just thinking like you can stick any kind of bit pattern in a binary, and so that you might be able to use that to encode a complex number in a single, say, 64-bit binary value, well, I guess, in order to minimize the amount of boxing and unboxing of tuples.
I guess, well, I mean, I suppose the answer is yes, insofar as like everything comes down to binary. So obviously you can. I guess the trade-off with that would be you'd have to create more help functions to pass the string, I imagine. Whereas I guess Elixir gives you these very easily, all these readily defined functions, or rather they have pattern matching, which makes it super easy. In that sense, I feel a tuple is like the ideal way you might do it for Elixir, but I'm not actually all that sure. I mean, I'm sure there's all sorts of ways you could do it, but a tuple does seem like a pretty obvious way in my mind, because you want these, because like the A and the imaginary part and the real part are they can't in some sense meld. It's only through multiplication that they kind of interchange roles. when you're just adding them, they're kind of very separate. In some sense, it's like having two axes on a plane, you know, the X and the Y axis. In fact, if anyone here is like familiar with complex numbers, they might be familiar with what I think is called an Argand diagram, where literally the real part is on the X axis and the Y part is on the and the imaginary part is on the Y axis. So having something that kind of represents a coordinate system, I think is like the best way or the easiest way to do it.
Yeah, using it could help express this absolute value as a square root of squared imaginary plus squared real. Then you don't have to use that arctangent cosinus cosine sine.
Yeah, so that was what I was saying before. That way, to get the value though, you need the square root function, which, as I was saying before, I was struggling with because I was thinking in TypeScript and I couldn't work out why I wasn't compiling properly. And then I figured out I was using the wrong expression for square root. Because to get the absolute value, you get a squared plus b squared, and then you have to square root that. Because a squared plus b squared would be the square of the absolute value.